In this video, I'm going to show you how to calculate related rates with cones. So here's our first problem. In a construction site, dirt is piled in the shape of a cone. The base diameter of the cone is always 1.5 times the height of the cone. If the height of the pile is increasing at the rate of 2 meters per minute, then at what rate is the volume of the pile growing when the pile is 4 meters high? First of all, what is it that we want to find? Well, we want to find the rate at which the volume of the pile is growing when the pile is 4 meters high. So that means we want to find dV dt, the rate of change of volume with respect to time. And we want to find that at the particular moment when the pile is 4 meters high. So when h, the height of the pile, is equal to 4. Okay, so this is what we want to find. But before we get into that, is there any other information we're given in the problem? Well, we're also told that the height of the pile is increasing at the rate of 2 meters per minute. So that means that dH dt is equal to 2. And what other information are we given? Well, we're also told that the base diameter of the cone is always 1.5 times the height of the cone. So let's write that down here. Diameter equals 1.5 times the height h. Okay, great. So we've taken inventory of all the given information, and now let's think about pulling apart this derivative into something that we can compute. So dV dt we will write as dV over something times something over dt. And we know what dH dt is, so why don't we fill in this something with dH. Now the problem reduces to figuring out what is dV dH. And in order to do that, we need to construct an equation relating V and H together. So why don't we start with the volume formula for a cone? The volume for a cone is that volume is 1/3 times the base area, which is pi r squared, because the base is just a circle with radius r, then times the height of the cone. But we want to find dV dH, which means we need our equation to just have V and H as variables. We don't want r as a variable. So what can we do? Well, why don't we use this relationship between the diameter and h? We know that the diameter is just twice the radius, so we have 2r is equal to 1.5 h. So we can solve for r in terms of h, just divide by 2 on both sides, get r equals 0.75 h, and then that's what we can plug in for r here. So volume is equal to 1/3 pi times 0.75 h squared times h. Why don't we actually write this as a fraction to keep it a little bit easier to work with? So volume is equal to 1/3 times pi times 0.75 is just 3/4. That times h, then squared, then times h again. So that means volume is equal to 1/3 pi, and then 3/4 squared, that's just 9/16, and then h squared, and then times h. So simplifying, volume is equal to, first of all, 1/3 of 9/16 becomes 3/16, so 3/16, then our pi, and then h squared times h is h cubed. So now we can take the derivative, dV dH, and that's equal to, just use the power rule, bring down the 3, you get 3 times 3 is 9/16 pi h squared. So that means dV dH at the moment when h equals 4, that's going to be equal to 9/16 times pi times 4 squared, and 4 squared is just 16, so that'll cancel out with the 16 in the denominator, and we'll just have 9 pi. And this is all the information that we need. So dV dH, that's 9 pi. And we're going to put that in for dV dH in the equation here. And dH dt, that's 2. So put that in for dH dt in the equation there. So that means dV dt at the moment when h equals 4, that's equal to dV dH, which is 9 pi, and then times dH dt, which is 2. And simplifying, that just makes 18 pi. And what's our units? Well, units of volume is units of length cubed, and units of length were meters, so meters cubed. And then that's volume per unit time, and time is measured in minutes. So there we go. That is the rate at which the volume of the pile is growing when the pile is 4 meters high. It's 18 pi meters cubed per minute. Here's our next problem. A conical container is being filled with shaved ice to make a snow cone. The height of the cone is 12 centimeters and the radius at the top is 5 centimeters. If the shaved ice is entering the cone at a rate of 25 centimeters cubed per second, then how fast is the height of the ice increasing when the ice has reached a height of 6 centimeters? So here we've got our diagram. It's an upside down cone that's filled with shaved ice here. The shaved ice itself makes a cone with radius r and height h, and that fits within the conical container which has radius 5 and height 12. We want to find how fast is the height of the ice increasing, so that's dh dt. And that's at the moment when the ice has reached a height of 6 centimeters. So at the moment when h equals 6. So what is this? Well, before we get into that, let's take inventory of what else we know about the problem. We're also told that shaved ice is entering the cone at the rate of 25 centimeters cubed per second. So that means the volume, V, of the shaved ice is changing at a rate of 25 centimeters per second. So dV dt is positive 25. So let's go ahead and jump into pulling apart this derivative. We'll pull it apart into dh over something times something over dt. Now, what should the something be? Well, we know what dV dt is, so why don't we let that something be dV? And now we know what dV dt is, so the problem just reduces to finding dH dV. So we need an equation relating V and H. Why don't we start by just writing the volume formula? For a cone, V, the volume, is equal to 1/3 times the base area, which is pi r squared, then times the height, which is h. But we just want an equation relating V and H. We don't want the r in the equation. So is there any way that we can get rid of the r? Can we write r in terms of h? Well, yes, we can. We can do that using similar triangles. You'll notice that in the diagram here, the triangle consisting of sides r and h is similar to the triangle consisting of sides 5 and 12. And in similar triangles, the ratios of side lengths are conserved. So that means the ratio r to h is equal to the ratio of 5 to 12. So multiplying both sides to solve for r, multiply by h on both sides, and you get that r is equal to 5/12 times h. So we'll go ahead and put that into our volume formula. Volume is equal to 1/3 times pi times r squared, and r is just 5/12 times h, and then that times h. And then we just simplify. So volume is equal to 1/3 pi times 5/12 squared, which is 25/144, times h squared times h. So let's simplify a bit. But actually, let's leave out this 1/3 instead of multiplying it in, because when we use the power rule, we'll have an h cubed and that'll cancel with the 1/3. So 1/3 pi times 25/144 h cubed. Take the derivative, dv over dh, and using the power rule, this is 1/3 pi times 25/144 times 3h squared. And we see that the 1/3 and the 3 cancel. So that means dV over dH is equal to, in the numerator, we've got 25 pi h squared. And then in the denominator, we've got 144. But we want dH dV, so we need to flip this, take the reciprocal. So dH over dV, that is equal to 144 over 25 pi h squared. Okay, great. So we've got dH dV. Of course, we want to evaluate that at h equals 6, but we'll do that when we plug it in to our product here. So this is going in for dH dV here, and then 25, that's going in for dV dt. So we get that dH dt at the moment when h equals 6, that's equal to dH dV, which is 144 over 25 pi times h squared, and h is 6 in this case, that times dV dt, which is 25. And we see that some things cancel. This 25, 25, those cancel. And now we've just got 144 over 6 squared is 36, so 36 pi. And 144 over 36, that is just 4. So this comes out to 4 over pi. And what are the units here? Well, this is dh dt. H is the length in centimeters, and t is a time in seconds. So there we go. That is how fast the height of the ice is increasing when the ice has reached a height of 6 centimeters, 4 over pi centimeters per second. So now we see how derivatives can be applied to calculate related rates with cones. And in the future, we'll continue to learn about more useful applications of the derivative, including approximating values of a function.